The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and welcome to this webinar on electrical safety tester verification. I'm your host, Syed Abidi, and this is the third webinar in our 2014 series of webinar. I will be presenting this webinar. Also helping us on the panel is Jim Kensey, who's the host, and Nick Piotrowski, who will be answering any questions related to the material being presented on the webinar. A few webinar notes before we jump into the actual material. As always, we have our Q&A utility, so you can ask us any questions concerning the material being presented through this utility. Any questions related to running of the meeting, technical support with audio or visual, etc., can be addressed to our host, Jim Kensey, also through the chat line. And just like all our other webinars, this webinar will be recorded and available to view within a day through our website. If you would like a copy of this presentation, please contact Jim Kensey again via the chat line or email him at jimk@asresearch.com. So with that said, I think we have enough people on board to go ahead and jump into this webinar. Before going into the material for this webinar, I'd just like to do a quick recap of the previous webinar that we did this month on the 12th, which was on the electrical safety testing, a complete overview part 2. And just to quickly recap what we covered, we went, if you guys remember, for those of you who did attend this, we went over some of the basic electrical safety tests, and then we tried to understand some testing requirements, gave some examples from the standards. Then we went into giving you guys some tips and suggestions on finding the right testing device for your particular testing needs. And then we gave out some tips and suggestions on things that you're not supposed to do during electrical safety testing, some safety tips and some important information to better assist you guys with your testing. So here was the recap, and once again, this is the third webinar in our 2014 series of webinars, and this one is on electrical safety tester verification. And here's an outline of what we will be covering today. First of all, we're going to try and understand what is a verification test, why is it required, what's the importance of it. Next, we're going to quickly review the 5 most common types of electrical safety tests that we already did in our last webinar, but we're going to go over these again. That includes the ground bond, the ground continuity test, the Hipot or the dielectric withstand test, the insulation resistance test, and the line leakage test. Also, along with going over these test types, we're going to also go over and suggest some ways of verifying each and every test, or each and every tester. If you have a all-in-one tester, we'll give you suggestions on how you could run verification tests on your tester to ensure that your test unit is working within specs and working properly as it's supposed to. We'll give you some examples of that, and then I'll have a little video demo of showing you guys how we can run some verification tests on our safety testers. And at the very end, we will leave the forum open for any questions that you may have, and Nick Piotrowski will be assisting you on the chat line, and I can answer any questions at the end of the webinar as well. So once again, feel free to ask any questions during the webinar using our chat line, and any technical support issues with the webinar or the audio or the visual, feel free to contact Jim Kennedy. Okay, to start with, what is a verification test? Well, it is a procedure to ensure that a safety testing device will properly detect product or DUT failures. Basically, verification of electrical safety testing equipment is a procedure which is often overlooked by manufacturers. And as we already know, an electrical safety test is only as good as the tester itself. A defective tester can lead to inaccurate or incorrect safety tests, hence passing or failing, giving false pass and fail results, and which can lead to improperly tested products being out in the market, posing all kinds of electric shock hazards to the end users. Running test verification is very crucial to ensuring that a safety device will properly detect product failures. Now, while the task of setting up a test verification can seem daunting at times, it's just a simple matter of having the necessary equipment and procedure in place so that the process is easy to follow. Verification tests are often required by safety agencies such as UL, IEC, and TUV. And by running these tests, initially, it's a time investment up front, but it pays off greatly by avoiding bigger issues and problems later on. According international safety testing agencies such as UL and the Canadian Standards Association, or TUV and IEC for Europe, they've all set forth various standards to ensure that electrical devices meet set requirements for electrical safety. Now, performing an electrical safety test is done to ensure that an electronic product does not pose a shock hazard to the end user. And also, an electrical safety test, however, as it's only as good as the tester being utilized on the product. And due to the nature of manufacturing environments, electrical safety testers can get damaged internally without showing physical signs of any damage. So as a result, these damaged units can give incorrect readings, and with regards to the in the insulation resistance or the leakage current. So therefore, performing regular verification on electrical safety testing equipment ensures that the unit, the tester itself, is operating properly, and you are testing to the NRTL standards. According to the UL Mark Integrity Program or document titled Equipment Used for UL-C-UL/ULC Mark Follow-up Services, all measurement and test equipment must go through regular inspection. Well, inspection, the IMTE, inspection, measuring and test equipment used to verify compliance with the UL requirements shall be checked daily by the customer to ensure it is functioning properly. If this equipment is not used daily, then this function verification should be performed prior to use. That is a very, this basically excerpt from this standard shows the importance of running a verification test, and it outlines the importance of maintaining and verifying measurement equipment, which includes electrical safety testers. And also you could see that from this excerpt, it outlines the importance. This program is basically the driving force behind the requirements to run regular verification on electrical safety testing equipment. In this webinar, we will go over some of the most common electrical safety tests and then run verification and show you how you can run verification tests on different types of testers. So once again, why do we perform verification tests? To ensure that the safety testing device is identifying true failures and faults in the product. It is required by safety agencies, and due to the nature of manufacturing environments, electrical safety testers can get damaged internally. Harsh environmental conditions such as heat and humidity can contribute towards electrical safety tester damage over time, and these conditions can affect the instrument's readings and accuracy. So it is hence making it possible for getting false pass and fail results. Whereas no visual signs of damage may occur on your tester, so there's no way of visually inspecting your tester. The best way is to run daily verification tests on your electrical safety testing device to ensure that it is working properly. Okay, so we're going to visit or review, I would say, our five of the most common types of electrical safety tests, starting with the ground bond test, the ground continuity test, the dielectric withstand test, the insulation resistance test, and the line leakage test. I know we've gone over these in our last webinar, so this, for those of you who were there for our last webinar, this would be a good recap. But for those who were not there, we'll go into enough detail so that you guys understand what these tests are meant to do and how these are run. Before going into our electrical safety test types, one thing to remember is that most of today's electrical safety testers, such as the Omnia 2 unit by Associated Research, which is an all-in-one unit, it basically allows you to run all types of electrical safety tests that we just listed. And due to the various different functions of the unit, it is very important to determine if the tester will fail properly. And especially in a high volume production setting, it is very easy to miss a unit that should have failed due to a bad tester. Therefore, there is the need to perform verification on all unit functions is important. Here are some efficient verification processes that we're going to lay out for you. Basically, electrical safety tests are designed, as we all know, to identify fault insulation, improper grounding, loose connections, defective parts, ground faults, unguarded live parts, and excessive leakage current. A good way of running a verification on these tests is by shorting or creating an open between test leads, just to verify basic failures, but not all potential issues will be detected with this basic method. So it's really up to the user how detailed you want to be with when it comes to verifying your tester. But what we're going to lay out for you in this webinar are some basic means of verifying your electrical safety tester and seeing that if it's measuring the correct leakage or measuring the correct impedance, and etc. Well, using resistive networks and relays is basically a quick and fast way for detecting if a tester is failing properly or detecting failures and passes properly. For example, the TVB2, the Test Verification Box 2 by Associated Research. Here's a picture of it. Allows the user to basically run a very basic verification for their ground continuity, ground bond testers, dielectric withstand AC and DC testers, also insulation resistance testers. We're going to get into some detail on how this box can be utilized when we give out some examples. But before that, this box basically consists of a series of resistors which are designed to draw a specific amount of leakage current. It allows the user to test in a simple pass-fail criteria and can be used with most of Associated Research testers. And here's a table laying out some basically resistance values and test settings for this. A simple and yet effective procedure can be set up, which can be run on daily basis using this box. And again, each test type verification on this box contains, as you can see, 2 posts, one for pass and one for fail. This is achieved by connecting separate resistance values from each post back to the return post on the box. We're going to get into that as we move on in this webinar. So back to our common electrical safety tests. We're going to start with the dielectric withstand, or the Hipot test. So basically, the Hipot test is run to stress the insulation of a product under test. It is commonly referred to as Hipot test because basically it's a high potential test, and it's designed to stress the insulation of a device beyond what it would encounter during normal use. The logic behind this test is that if the device can handle the force of a very high potential for a short duration, it should be able to operate at rated voltage without posing a shock hazard to the user. The Hipot test is a very versatile electrical safety test because not only it is designed to test the weak points in the insulation, it can also be used to measure excessively high leakage current, workmanship defects such as pinholes and scrapes, improper spacing with respect to a grounding point, and just natural degradation due to environmental conditions. Due to this very versatility of this test and the fact that this test can detect a number of insulation faults, this test is generally specified as a 100% production line test. Again, this is the production line and type test is from something we covered in our last webinar. The method of running Hipot tests involves applying high voltage across the current carrying conductors with a return point on a conductive chassis. The Hipot unit will measure the resulting leakage current flowing through the insulation, and the potential used in the Hipot test varies from standard to standard, but a common formula for calculating Hipot voltage is to take 2 times the rated voltage of the product being tested and add 1000 volts to it. So the formula becomes 2 times rated voltage plus 1000, which will be your Hipot test voltage. Again, this varies from standard to standard, so it's always a good idea to refer to standards when trying to set test parameters for electrical safety tests. Okay, so next, now that we've gone over what is dielectric withstand test and what does it do, what does it test, and how is it run, we're quickly going to go over how can we run a verification test to verify that our Hipot tester is working correctly and measuring leakage and breakdowns correctly? Well, once again, we're going to go over a basic verification method, and we're going to use our example of the TVB2 box, the test verification box that we just discussed, which is a simple go, no-go box for running daily verifications on your electrical safety testers. So in this, here we're going to use the TVB2 as an example, and we're going to use 1240 volts AC as our example. We're going to refer back to our table for the TVB2. So we're going to use a voltage of 1240 for an AC test, and as we know, the fail circuit in this box includes a 120,000 ohm resistor, and the pass circuit utilizes a 2 mega ohm resistor. So we have a 2 meg and 2 meg on the pass side and 120 k ohms on the fail side. So the Hipot unit would then be set for two separate tests. One will be for a pass and one will be for a fail. The first test is a pass test. Go back to the box, you could see there's a pass and a fail port for each test type. So the Hipot unit, as we know, is set to a 1240 volts AC. We're going to set a high limit, and that's all based out of the table that I just showed you, and this information is available to you guys via our website, and again, you can contact Jim Kennedy to send you a copy of this presentation. But here our test, our high limit for the trip current is 10 milliamps. We're going to do a 2-second ramp up time and a 1-second dwell time. The high voltage lead from the Hipot unit, go back to the TVB2 box. So what we're going to do is, the way we're going to connect our tester is that we're going to connect the high voltage lead from the Hipot unit to the pass terminal on the ACW/DCW side, as you can see for the dielectric withstand test, and we're going to connect our Hipot unit to the pass terminal on this portion of the TVB2 box, and the return lead is connected to the return terminal of the TVB2, which is the black terminal in the very center of the box. Using now, if we use simple Ohm's law calculation, it can be determined that the leakage current should be around 620 microamps. So if we do a quick calculation using the Ohm's law, current equals voltage divided by the resistance. In this case, our voltage is 1.24 kV divided by 2 mega ohms, so we get around 620 microamps. This should be the result. This should result actually in a test pass. So this will tell us if the leakage current is close to this value of 620 microamps, this means that our tester is detecting a true pass. So here we verified the pass condition for our safety tester. Next, we're going to do the same procedure, follow the same procedure to run a verification for the fail side. So then, this time we're going to have our high voltage lead is then moved from the pass side on the TVB2 box to the fail side, because we're trying to verify if our tester is going to fail correctly. Therefore, when the test is run, and we're going to use pretty much the same parameters, the same voltage of 1.24, but this time on the fail side our resistance is different, it's 120K. So if we do a quick calculation, we should be seeing a current of around 10.3 milliamps. And when we run this test, the test should fail within 0.5 seconds of the dwell cycle. Hence, that would tell us that our tester is detecting proper failures, true failures and true passes. in order to keep in specification with the agency regulations, the test should fail within 0.5 seconds of the dwell cycle. If the test does not fail, the unit your electrical safety tester that means it's not properly reading leakage current and should be repaired or calibrated. So here we go. This is how we would recommend you use the TVB toolbox to run a daily verification test on your safety tester. Okay, next we're gonna quickly review the ground bond test. The ground bond, or the ground continuity test, is used to analyze the integrity of the safety ground on an electrical device. Now remember, this test is meant for class 1 products. Class 1 meaning products which have a ground pin in their power cord, which have a ground circuit. So ground bond and ground continuity tests, they're used to analyze the integrity of the safety ground on an electrical device, and also the ground continuity test checks basically tests for continuity of the ground circuit. The safety ground needs to be able to handle any fault currents that could be imposed upon it due to a product or insulation failure. So basically, a low impedance path to ground will allow circuit protection devices such as fuses or circuit breakers on the input to react immediately to protect the user from dangerous electrical shock. Now, in order for the system of protection to operate effectively, there must be continuity between the conductive components of the product and the product's ground pin or the ground terminal. The ground bond tester, the way this test works is, now again, this is an review of what we've already gone over in the last webinar. The way ground bond test works is that the tester injects a current into the ground pin of a product, and then it looks for a return path on the chassis or the exposed dead metal. Simultaneously, the instrument must also measure the voltage drop across the safety ground circuit to calculate the impedance of the circuit. Common ground bond parameters are for a current of between 10 to 30 amps with a maximum impedance of not more than 100 to 200 milliohms, and the voltage drop is not to exceed 12 volts. Again, these parameters are just the most common parameters, but again, we highly recommend that if you are trying to set test parameters, always consult your safety testing standard that you're trying to comply with to set the correct parameters. Okay, so next in line is how would we, now that we know what ground bond test does and how it's performed, how can we verify if our ground bond tester is working fine, it's measuring correctly? Well, once again, we're going to use the example of our TVB toolbox. I'm going to go back real quick to show you. If you see the GB on the bottom left side of the box, you see a ground bond for GB, and you'll see on the fail side there's a 200 milliohm, and on the pass side we have a 50 milliohm. So we have a fail and a pass, and also the return port in the center that we're going to utilize here. Okay, so in this example, we're going to use a test current of 25 amps AC. If you go back, and again, this is directly out of that table that I just showed you. Let's take a quick look here again for the ground bond parameters. Instead of 30, we're going to be using a current of 25 amps for this example. That, shouldn't make a big difference here, but the fail, if if you saw on the table, the failed circuit includes a 200 milliohm resistor and the passed circuit utilizes a 50 milliohm resistor. So the ground bond unit would then be set similar to the Hipot test. It will be set for two separate tests. The first test is the pass test. So for this test, the ground bond unit is set to 25 amps, a high limit of 100 milliohms, and a potential drop of 6 volts. We're going to use a 1 second ramp up time, 1 second dwell time. And so the high current lead from the ground bond unit will now be connected to the pass terminal on the ground bond portion of the TVB2 box. And the return lead is connected to the return terminal of the TVB2 box. When the test is run, the resistance should be around 50 milliohms, which should result in a test pass. And similarly, the next test would be a fail test with the ground bond unit set to the same parameters as the pass test. This time the high current lead is then moved to the fail terminal on the ground bond portion of the TVB2 box. When this test is run, the resistance should be around 200 milliohms, which in return should result in an immediate test failure. Now, to keep in specification with the agency regulations, this test should fail within 0.5 second of the dwell cycle as well. If the test does not fail, once again we know that the unit is not properly reading the resistance value and should be analyzed or sent back for repairs or troubleshooting. So that was the ground bond test and a basic way of how the TVB2 box can be used to run ground bond verification. Okay, next in line is the insulation resistance test. Now, this test is similar to the Hipot test. It is basically the least commonly specified electrical safety test, but yet it can provide the user with some valuable information about the product being tested. Whereas the Hipot test provides a leakage current value, the insulation resistance test gives an actual resistance measurement of the insulation of the product itself. So this is where the test is different from a Hipot test. Also, it's not run at a very high potential compared to the Hipot test. It's stressing the same insulation, but at a slightly lower voltage, which is specified by safety agencies to be between 500 volts DC to 1000 volts DC. Now note that since the Hipot test can be either AC or DC, the insulation resistance test potential is DC in nature. So this basically, when this test is run, once the capacitive portion of the insulation has charged, the only leakage current flowing through the insulation will be resistive in nature, and thus it will allow the user to measure an insulation resistance value. Also, the insulation resistance test is run in much the same way as the Hipot test. The high potential is applied to the current carrying conductors of a device and the return point of the circuit to the chassis, just like the Hipot test. So yeah, it's very similar in nature to the Hipot test, but gives some other important information, gives out an actual reading for the resistance or the impedance of the insulation of the product being tested. Next, we're going to see how, now that we know what is the insulation resistance test and how it can be run and what does it, what information does it provide the user, we're going to try to see if we can come up with a way of verifying whether our insulation resistance tester is working within specs. So we're going to use our again are the TVB2 box, and again for the insulation resistance test, there's let's go back to the picture real quick here, and you'll see on the bottom right corner this time IR. That's the portion that's going to be used when insulation resistance test verification is run using the TVB2 box. Again, you can see there's a fail port and a pass port. The fail side has utilizes a 1 mega ohm resistor, the pass side a 4 mega ohm resistor, and once again the return port is going to be used for our verification. So for this test, in our example, we're going to be using a voltage of 500 volts, and again this is back from the table that I just showed you earlier. And we know that the fail circuit includes a 4 mega ohm resistor, and the pass circuit uses a 1 mega ohm resistor. So the IR, the insulation resistance tester, or the unit, would then be set for two separate tests, just like the ground bond verification and the Hipot verification. The first test is a pass test. So the IR unit is set at 500 volts DC. And we're going to set a low limit of 2 mega ohm and a 2-second ramp up time, a 1-cycle dwell time. The high voltage lead from the insulation resistance tester connects to the pass terminal on the IR portion of the TVB2 box, and the return lead is connected to the return terminal of the TVB2 box. When this test is run, the resistance value should be around 1 mega ohm, which should result in a test pass. Now similarly, the next test would be a fail verification. So this time the insulation resistance tester is set to the same parameters as the pass test, but the high voltage lead is moved from the pass side to the fail terminal on the TVB2 box for IR test. When the test is run, the resistance should come out to be around 4 mega ohms, and it should register an immediate fail. Now once again, in order to keep in specification with agency regulations, this test should fail within 0.5 seconds of dwell cycle. And if it does not fail within this time, the unit needs to be looked at and analyzed for faults or defects. Okay, so that was insulation resistance test and how we can run a verification test on an IR tester. Next is line leakage test. The line leakage test, just like the Hipot test, measures current flowing or on the surface of the insulation on a device. However, the line leakage test differs in that this measurement is actually performed while the product is running at rated voltage, or maybe a high line condition of 110 volts of rated, 110% of rated voltage, as specified by the standards. The other major difference between how the leakage current is measured is that for a Hipot test, the leakage current is measured through a current sensing resistor on the return side of the circuit. But during a line leakage test, the leakage current is measured through what we call a measuring device, or an MD. A measuring device is basically designed to simulate the impedance of the human body. So another aspect of the line leakage test that sets it apart from other electrical safety tests is the fact that it incorporates fault conditions. These fault conditions are designed to simulate worst-case scenarios that could happen during instruments operation. And the three most common fault conditions are the opening of the neutral circuit, the reversal of line polarity, and opening of the ground circuit. Now, line leakage parameters can vary greatly from standard to standard. However, some of the most commonly run line leakage tests are for compliance to the 60601-1, which is the the safety standard for medical devices. For this standard, line leakage tests must be run at 110% of line voltage, and the acceptable leakage current values can range from all the way to 10 microamps and up till 10 milliamps. So here's next we're gonna try and see if we can come up with a way of suggesting an efficient way of verifying whether our line leakage tester is functioning properly or not. Well, line leakage verification, and let's go back to the TBB2 box, and if you guys notice that the TBB2 box allows the user to run verification tests on ground bond, ground continuity testers, Hipot testers, both AC and DC, insulation resistance testers. But, however, if you notice, you may not have seen any line leakage verification ports on that box. And the reason why that is because line leakage verification is not as well defined as verification for other test types. And we already know that the TBB2 box does not contain terminals to test for line leakage values. However, the same concept can be used or applied to ensure that the line leakage unit is operating within specified values. Since a product is operated at rated voltage during line leakage test, most line leakage testers, they include a universal power receptacle, similar to the one shown in this picture at the very bottom. This is one of the power receptacles that Associated Research sells with its leakage testers, and this box can be used for running multiple different types of tests, and it's compatible with the Omnia 2 series of complete electrical safety compliance analyzers. So if you look at this box, you'll see a line, two white cords. One is for line, one is for neutral, and the red cable is for the ground connection. So a simple fixture can be made using this adapter box. So if you think about a standard plug which terminates into two separate resistor values of creating a line leakage verification test. So basically we can utilize simple resistors and place them between ground and line, and to see if the leakage tester is measuring the correct leakage. Since the leakage meter reads between ground and neutral for normal polarity and ground and line under reverse polarity, separate resistor values can be wired between line to ground and neutral to ground. So for example, what we can do here is for line leakage verification, a plug can be wired with a 2 mega ohm resistor between line and ground, and also a 200 mega ohm resistor between neutral and ground. So we have a 2 meg between line and ground and a 200 meg between neutral and ground. So the first leakage test is set to run in our example at 120 volts AC, 60 hertz, 50 microamps would be set as a high limit, and we're going to set reverse polarity. We're going to have a 5-second dwell time. Now with a 2 mega ohm resistor from line to ground, the leakage current can be calculated. So Once again, using the Ohm's law, the leakage current comes out to be 120 divided by 2 megs, which is 60 microamps. If we run this test, this leakage current should produce a failure on the test because our high limit was set to 50 microamps and we're going to see 60, around 60 microamps. So this should result in a fail, hence telling us that the leakage tester is calculating leakage current accurately. The second test would be to check for a failure under normal polarity condition. So the second line leakage test will be set to run at 120 volts AC, again 60 hertz. This time we're going to set a high limit of 550 microamps, and we're going to have normal polarity, again a 5-second dwell time. Now using a resistor, a 200 mega ohm resistor will be wired from between neutral and ground, and the leakage current value, if we calculate it, should come out to be 600 microamps. This should produce a failure on the test, and that would tell us that this our electrical safety tester is measuring or reading correct failures and passes. Now, while a line leakage tester can also, it usually does contain various other relays, the main idea here was to show that the leakage detectors on the instrument fail in the presence of excessive leakage current. The two tests that we just outlined for verifying line leakage testers, they kind of prove that if the line leakage, that if a line leakage meter is properly, whether it's reading leakage values properly or not. Next, we're gonna go over real quick two video demos that I have for you guys showing how the TVB toolbox can be used for verifying your electrical safety tester. Let me pull up those videos for you guys real quick. So here, I'm going to play a video, and I'm going to pause it for a second just to tell you guys what we're going to be seeing here. Basically, in this picture, what you're seeing is this is our Omnia 2 electrical safety compliance analyzer. This unit is capable of running all the tests that we've discussed thus far, starting from ground continuity, ground bond, AC, DC withstand, insulation resistance, and all types of line leakage tests. And here you can see we have our TVB toolbox hooked up to the Omnia unit. The first test that we're going to run here is to verify the ground continuity, and the next one would be, within this video, the next test would be how we can use the TVB toolbox to verify the ground bond test. If you can see in the picture, the two red cables, sense and current, they're terminated into an alligator clip that's connected to the pass side of the ground continuity, and the black return and sense cables that are also terminated into a alligator clip on the other end is connected to the return side of the TVB toolbox, as we discussed earlier. I'm going to go ahead and also we've pre-programmed a test sequence in the Omnia tester and saved that sequence. So all we need to do now is to press the test button and see if our tester is passing and failing accurately. So here we go. We're going to press the test button, and we have a little prompt that says this is a pass test for continuity. And as you can see, I'm going to go back for a second here. You can see that the result is a pass. It's getting a resistance of 0.63 ohms, hence resulting in a pass test. Next test is a ground continuity fail. As you can see from the prompt, you push the test button, you get instantly a high limit failure. Go back here real quick. Sorry about this. So this is the high limit failure for the continuity. Next, we're going to quickly move our cable from the ground continuity to the pass side of the ground bond, run a 30 amp test, and see. We get a pass. Next, we switch to the fail side of the ground bond test, and we get an instant failure. And then if you go back to look at the results, that's a continuity test, pass, fail, ground bond pass, ground bond fail. So this is how the TVB toolbox can be used to run to verify your ground bond and ground continuity tester. Next, we're gonna run a quick verification to verify the AC withstand, the DC withstand, and the insulation resistance test. Once again, the Omnia unit was pre-programmed with the test parameters that we discussed in our examples that we went over just now. So all the steps are ready. All we need to do is we're going to start with I think the AC withstand verification. The pass side first. As you can see, the red, the high voltage cable is connected to the pass side, and the return from the Omnia is connected to the return on the TVB toolbox. So here we go. We're going to start with the AC test, pass fail, then we're going to do a DC pass fail, and then the insulation resistance pass fail. You can see prompts on each step telling us what tests are we running. So here's the AC withstand pass. Now we're going to connect to the fail side of the AC. Here's a prompt for that. We press the test button, and within 5 seconds we're getting a high limit failure. Hence that's telling us that's a true pass. Now we're going to run a DC Hipot test. And this is the pass test. As we can see, we get a pass with the limits that we set. Now we're going to do a DC Hipot fail test, and the test failed right away. Next, we're doing an IR, insulation resistance pass side, and we get a pass. We move the high voltage to the fail side, IR fail test is run, and we get a failure instantly. So we're going to quickly go through the results for AC pass, AC withstand pass, AC withstand fail, DC withstand pass, DC withstand fail. As you can see on the left, it may not be very clear, but the tests that are laid out in red were fails, and the ones in green were passes. That's how the Omnia displays the results. So here was our line leakage verification and the video demo. Having gone over all this information, I think we're approaching the end of our webinar. Just to conclude here, we all know that with the advancement in technology and the advent of microprocessor technology and electrical safety testing units, setting up instruments for test verification has become very complex. Now, if you think about merging technology on the units, it requires more in-depth test verification than an old analog device. Think about the line leakage tester. I mean, think about all the MDs and all the different fault conditions and etc. in a leakage tester. The verification method that we went over for line leakage test was a very basic verification to see if the leakage measurement is being done correctly, which this test that we went over, it should verify that much for you. But once again, you can go in a lot more detail and design or come up with your own verification processes. Of course, we can help you guys out with that, but it really depends on how much detail you want to get into. Additionally, electrical safety testing instruments contain built-in suppressors that are designed to protect the unit circuitry. So, but at the same time, these are electrical devices after all, so damage to such suppressors can cause false readings on an instrument. But taking simple steps to run daily verifications, like the ones that we went over, can spare a great deal of trouble and effort down the road, and can help avoid costly redesigns or product recalls. Think about, a bad product being out in the market and somebody, the end user, getting shocked or injured. That could lead into huge issues with companies being sued. So this kind of stresses the importance of running verification tests on electrical safety testers, because once again, an electrical safety test is only as good as the tester itself. Using a simple resistor in series with the output of an electrical safety test equipment, it will assist in validating measurements and ensuring that the failure detectors are functioning properly. Setting up fixtures with a series of resistors, calibrated resistor values, it takes the verification process one step further, and this is where the TVB toolbox that we went over comes in. Additionally, microprocessor controlled safety testing devices, they now allow for programming and saving verification procedures, just like in the Omnia, that test file that we use, that can be saved in the unit or on your program, so that you don't have to create verification or program verification tests every day. You could just, connect your tester to the TVB toolbox or something similar, and just, with one press of a button, you'll be able to verify if your tester is working properly or not. And such procedures can be set up, to include working instructions and data acquisition. So if right now the demo that we showed you guys was just the Omnia being used via the front panel, but such procedures can be set up to include working instructions, just like we had in the prompt, and data acquisition. Verification methodology kind of gives the operator a simple means of storing the verification test procedure as well as running validations on a daily basis. So yeah, here at AS Research, we recommend, I personally like to, if I'm, run verification tests on my safety testers in my lab, at least once a day before I use them, just to make sure I'm not getting any false passes or fails. And performing regular verifications basically ensures that all equipment is working within the NRTL specifications and giving you correct leakage measurements and correct results. So with that, we're going to end our webinar right here and leave the forum open for any questions that you may have. Feel free to type these out on our chat line, or you could email us these questions as well. So yeah, we're going to leave the forum open for any questions right now. And in the end, I'd like you to go over our contact information once again. If you'd like a copy of this presentation, please contact Jim Kennedy at jimk@asresearch.com. Our phone number and our company email address and everything is listed on this page that you're seeing right now. I'd like you to make a note of these important numbers and emails. So if you need any assistance with any help with verification or any material that was presented in this, or any questions in general, feel free to contact us. I'd like to thank you all for your patience and time for attending this very important webinar on electrical safety tester verification. And I hope you will continue to join us in our upcoming webinars for for the 2014 series of webinars, because we're going to be covering some very important and very good stuff that anyone in the electrical safety testing industry should be aware of. So this is so again, yeah, the forum is open for any questions. Feel free to put them on our chat line or just email us.
Hey, Syed.
Hey, what's up?
Yeah, we got a question of just real quick. I just wanted to reiterate a point about the presentation itself. I got a couple questions on this on the question line. So if you email Jim, Jim will send you a copy of the PowerPoint. And then people were also asking about the full recording of the presentation. You can actually get that off of our webinar archive. If you go to our webinar archive, it should be up there by the end of the week at the very latest, I would think, and that will be the full recording. So you can get it directly from there if you wanted to view it in the future. And then there was an important point and question that somebody brought up early during the presentation, and basically what he was asking about the verification was, should you not use the cable assembly, test leads, DUT fixturing that you would have in your setup when you perform the verification? And I just wanted to make a quick point on that. There's a couple ways to look at this. Now, the short answer, in my opinion, is yes. If you do have special fixturing or leads that lead up to your DUT, I would include that in your verification test, because not only will that check that the Hipot or electrical safety tester is actually failing when it should fail, it's also showing you that there are no issues with your fixturing or your test leads or whatever the case might be. So for example, when I run a verification test in the lab on, let's just say, an Omnia unit, I will use the test leads, the high voltage and the return lead, or the current and return lead, that I will be using for testing, because that will also factor in if I have an issue with my leads. Then I can go back and troubleshoot and see, okay, is this a problem with my lead, or is this a problem with my unit by using a different set of leads, or what have you. So I do think it is a very good practice to use the fixturing and to use the any kind of specific fixturing or lead set going up to your DUT. So then instead of attaching your DUT, if you had some kind of special fixturing, attach the resistor or the TVB2 box instead that essentially acts as a DUT. And then what you do is you set your appropriate trip points, make sure that the unit fails when it should fail. Now there's something else that's important to keep in mind here. If you do have special fixturing, especially if it's very long cable lengths or a special fixture board that has its own leakage, that has to be factored in, because the TVB2 box, remember, is just passive elements. It's just resistors. That could affect the reading that you get on the unit. So it might not pass or fail at those set points should you have something that does increase or decrease the leakage current as a result of this fixturing. So it's something you really do have to pay attention to and play with before you decide on your proper verification procedure. And the bottom line comes down to risk analysis. You have to make sure on your setup, if there's a chance that a reading could be affected by your fixturing, that has to be accounted for. So I just wanted to address that because somebody brought that up early on, and it was a very good point.
Thank you, Nick. Once again, guys, any other questions you have pending, just feel free to email Jim Kennedy, and they will be forwarded to either myself or Nick, and we will be more than happy to answer any questions on this presentation, anything regarding verification, or any questions in general.
Hey, Syed?
Yeah.
We did get one here at the end, and basically it says, does the Omnia 2 have additional verification tests built into the unit separate from using the TVB2 box?
Mm-hmm. Well, the Omnia 2 has a way of running a self-verification, which is called the VeriCheck, which basically kind of self-tests the unit for to see if it's working properly. However, we would still recommend to use something like a TVB2 box, an additional external verification method, and use a test file dedicated for verification. But yeah, to answer your question, the Omnia does have a feature that's called the VeriCheck that allows the user to run a self verification within the Omnia itself. Okay, I guess we're not getting any more questions, but once again, if you guys have any other questions, feel free to email us. We're gonna close this presentation, and once again, thank you very much for attending.